Hello, everyone. My name is Gabriel Nicholson,
I'm John Omer.
and our other team member is Samuel Hobbs. We are students of Sonoma State University of the Department of Engineering Science. Our faculty advisor is Dr. Nansong Wu, and we are designing a automatic unmanned surface vehicle-based water quality monitoring system. Water is an important resource that both humans, animals, and even insects require for survival. Therefore, monitoring its quality is important for the health and safety of all. Today, most water quality testing is either done with stationary platforms or with manual handheld sensors. However, with unmanned surface vehicles and the integration of the Internet of Things, the strain on manpower and lack of coverage area can be addressed. After reviewing a number of different water quality monitoring projects, we have decided to implement the following sensors: pH, temperature, dissolved oxygen, and turbidity. In a review of 3 USVs, Vastavan, Yang, and Medeo, we see that all 3 use pH sensors, and at least 2 of these previous works use temperature and dissolved oxygen sensors. While turbidity is only used by the project done by Yang, it is an important sensor as it is a valuable indicator of solid and particulate pollution.
While researching what type of boat hull our team should go with, we ran across a theme amongst other related projects. A catamaran-style boat was used in the majority of these projects. By using 2 hulls instead of 1, the center of buoyancy of the USV is widened, allowing for increased stability. With this increased stability, our USV could theoretically withstand roll perturbation angles up to 84 degrees. Since smaller USVs can be greatly influenced by weather conditions, the team has decided to limit the weight to 46 kilograms and make it portable enough to fit in the back of a standard size SUV. As for the housing of the electrical components, our team plans to use an IPX4 rated box, which will be resistant to water splashes from any direction.
The Pixhawk 4 is used with a GPS module for navigation along a path. We've selected to use the Pixhawk 4 as our flight controller as it is known to be more accurate than the APM 2.8 flight controller. In our studies, we found that at most, the Pixhawk's accuracy was within 3 meters, whereas the APM's accuracy was within 6 meters. We've chosen an automatic approach via path planning software. By designing paths, we can approach water testing and sampling in a logical manner, specifically targeting areas of interest. As for the software, we have settled on MapProxy as it has much more available documentation than APM Mission Planner and supports Macintosh operating systems. For the wireless communication to the cloud from the USV, there are a few different methods of transmission: LPWAN, cellular, and WLAN. As can be seen in the figure on the lower right, WLAN has a very short range but high bandwidth. Cellular has a high bandwidth and a decently long range but high power requirements. LPLAN has the widest range of both of these and is also low power, but with less bandwidth, considering we are communicating sensor data and not video data or other large data. This is not really an issue to have less bandwidth. Of the available LPWAN platforms, LoRaWAN has no licensing cost. As such, we have chosen the low-stick USB LoRa radio transmitter device. Its main advantage over other solutions is that it is an all-in-one package that connects directly through USB. The LoRa module transmits the data from the USV to the base station, which is connected to a gateway to the cloud, where it is forwarded to a website for visualization.
Here is a 3D rendering of our vision of the USV's design. It is a catamaran-style boat that has 2 motors on each hull. The placement of these motors will allow the USV to perform differential steering. In the center of these 2 hulls is where we'll have our IPX4 rated housing. This is where the microprocessor, flight controller, and other vulnerable connections will be located. Here's our system block diagram via USB. They're broken down into separate modules: sensors, navigation, data, power, and base station. The base station is where we'll be issuing plan path to the flight controller in the navigation module. The flight controller will communicate with the GPS indicating its location, and with the motors will reach designated waypoints. At these waypoints, the flight controller will issue a command to the microcontroller in the sensor module. The sensor module is where we have our microprocessor and our 4 sensors. The sensor data is sent out to the data module and then is sent to the gateway located at the base station, where it then will be sent to the cloud. Given a review of these previous and related works that we have studied, we have settled on a hull design, sensors, flight controller software, and data transfer technology that we believe fits best to solve the issue of lack of coverage and awareness of water quality. In our future works, we will be building a prototype and conducting water quality tests to gather data, record the movements of the USV and check for accuracy compared to the planned path, and conduct additional research to improve both data collection, path plan following performance, and deliver an improved iteration. Thank you for your time.